Okay, welcome everybody. This is the first in a series of videos for Chemistry 1210 second midterm review. So we start with Chapter 5, dealing with energy, and actually the title of the chapter is Thermochemistry. So this first unit will just give some background information on what energy is, how we determine internal energy of systems, and the chemistry definition of the changes in energy of internal systems. So we start out by defining energy, and so energy is the capacity to do work or transfer heat. Work is that energy used to cause an object to move against a force. So work can change energy. So two basic types of energy that we talk about are kinetic energy and potential energy. So the formula to find kinetic energy is going to be E equals 1/2 times mass velocity squared. So that definition is from physics. Another type of energy that we see in chemistry is electrical or electrostatic potential energy. Electrostatic potential energy. And the formula for that is K, which is a constant, Q1, Q2, divided by the distance between the two charges. K is equal to a proportionality constant, which comes to 8.99 times 10 to the 9th joule meters per coulomb squared. So when solving for energy on these types of problems, you plug in your two charges and you figure out the distance between them, multiplying by the proportionality constant. So coming more to the chapter that we're focusing on here, thermochemistry. So we talk about the system and the surroundings. And so the things that we study, just do a quick example here. Say we have a system and we have this piston here. This is considered the system. Okay, so it is a system with gases in it and a Bunsen burner underneath. This is a Bunsen burner, and it can be used to add heat to the system. So within this piston, we have all these gaseous particles, and we call that the system. Everything else on the outside is called the surroundings. So this brings us to the first law of thermodynamics, which states that internal energy of a system is the sum of all the kinetic and potential energies of the components of that system. Okay. So energy in this change, the change is going to be defined as delta E equals the final energy minus the initial. Okay, hopefully that's legible. I'm trying to minimize the sound the pen makes. So we can't really determine, per se, the actual values of the final energy and the starting, but we can determine the change by applying the first law of thermodynamics. So delta E is related to heat and work. Delta E equals Q plus W. That is our starting formula for this chapter. So this basically means that all the energy within this piston over here is made up of any heat done on the system plus any work done on the system. Now, this system can lose heat and can also do work. So we get into something that a lot of students struggle with, called sign conventions. Okay. So for Q, we can have a positive value, and this means, so kind of imagine if we light the Bunsen burner, then we are depositing heat into the system. So therefore, heat must be added if it is to have a positive sign. Okay. Conversely, Q will have a negative sign if heat is released by the system. Again, I apologize for this writing. I hope that you all can read it. So heat is released from the system if Q is negative. So imagine just simply lighting the Bunsen burner, and if heat is going into the system, then Q is positive. And imagine putting your hands around the piston and holding it, and if it feels hot, then you know that heat is released, so therefore Q is negative. So we have another variable, and that's W. And we have a positive sign for W, and that's going to mean that work is done on the system. Okay. And here again, just think of it as we are adding work. We go back up to our plunger, to our piston, and if we push down on this, then we're going to be doing work on the system. So W will be positive. Conversely, W will be negative if the system does work on the surroundings. Okay. So the system does work on the surroundings, then we will have negative work. So you can consider that the work is being withdrawn from the system. The system is exerting effort, if you will, trying to do this work. So basically that would mean if we're standing on the top of this piston, then we would be pushed up. The gas would be expanding, and the lever would be pushed up, and so the system would be doing work on us, on the surroundings. The system can also, well, we told before, going back to Q and the conventions here, if Q is positive, then when you touch the outside, it will feel cold. Because if heat is released with a negative, that means that we have to add heat to make the reaction go. So one example of this would be if you injure your leg and you need to get an ice pack. And they used to have the old-fashioned ones where they had the powders inside, and you would crinkle the case up and then it would get cold. That is an example where heat must be added for the system to take place, or for the reaction to take place. So again, kind of going back to that idea. Oh, let's see, my pen just stopped. Let me turn this back on. Okay. Okay. Just 1 second here while we figure out this technical difficulty. I'll be pausing. We'll come right back. Okay, we are back. The pen had some technical issues. So if Q is a positive value, then we say that the reaction is endothermic. That is, heat is a reactant. If Q is negative, we say that the reaction is exothermic. That means heat is a product. Heat is released from the reaction, and it feels hot. So there are many fun reactions that are exothermic. The thermite reaction, any kind of explosion, any kind of combustion, those all release heat. They're exothermic. Okay, so the first problem that we will see will be coming up here. Okay, so this is our first problem for this section, and it is calculate delta E for the following cases. In each case, determine whether the process is endothermic or exothermic. So for this first one, it's kind of a nice warm-up. They give us both variables needed. So remember that our formula used is delta E equals Q plus W. So they define our variables for us, so it's very easy to simply plug those variables in and determine delta E. So Q is given as 0.452 kilojoules plus we are given negative 267 joules. Now, important point here, notice the units are different. Okay, we're working with kilojoules and joules. So you could set up a unit conversion to convert joules to kilojoules, but what I like to do is just simply multiply by 10 to the negative third, and that will put our units into kilojoules. So that's kind of a nice fast way of getting units to be the same. So now we are set to simply add. So I have my calculator here, and I'm going to add these together. Remember, you do have a negative number, so you have to make sure that you take into account that negative sign. Do not change the signs. So our answer is going to be 0.185 kilojoules. That's delta E. And the next question is determine whether it is endothermic or exothermic. So again, since we got a positive number for delta E, then you know that this process must be endothermic. Okay. Part B to this problem is a system releases 23.8 kilojoules of heat to its surroundings, while the surroundings, and this again is a little typo, the surroundings do 60.0 kilojoules of work on the system. So this goes back to our definitions from before in terms of sign conventions. So again, our basic formula is delta E equals Q plus W. So what's the Q in this case? A system releases heat. So that tells us the sign. So you have to read these questions carefully because they will tell you a variety of ways whether heat is released or added. So a system releases 23.8 kilojoules, so Q must be negative. Okay. Now that's Q plus W. So the surroundings do 60.0 kilojoules of work on the system. So we know that we will have positive work. So we simply add these two numbers. So we simply add, and our answer is 36.2 kilojoules. Okay. Now the overall system is going to be, again, endothermic because our final answer is positive. Okay. So this concludes the first type of problem, the first law of thermodynamics. We are just calculating internal energy from heat and work. See you in the next video.